Okay, thank you, Parveen. Very good evening to everyone. I am Sahil Gaurav. Here we are going to see this live tutorial session number 3 for the assignment 3. So we have seen in the last two sessions, we have in the first session, we have seen the problems based on the IV characteristics of PV cells, fill factor and efficiency of PV cell or module. And in the session number 2, we have seen problems based on the series and parallel connection of PV modules. And now in this session number 3, we are going to see the problems based on the solar insolation and the solar incident energy. So before that, before we begin to solve the problem, let us have a quick recap about some of the equations, some of the equations that will be helpful while solving the problem. So beginning with this solar insolation and efficiency of PV modules, we know that efficiency is the efficiency of PV cell or PV modules, that is ratio of output power upon the input power. And efficiency can be written, output power can be written as VMP into IMP if it is operating at maximum power point, that is its operating point, upon this input power is the solar insolation multiplied with the area of the PV cell. So this we have seen that these characteristics of solar PV cells, maximum power point voltage, maximum power point current, and this can be also efficiency can be also written in the terms of fill factor. Since fill factor is ratio of Vm Im upon VOC into ISC. So if we write in the terms of fill factor, then it will be coming like this. And the input power for the PV modules is the solar insolation and the area of the PV module, L into A. And the effective area for the solar insolation, we have to take the normal to this horizontal PV cell. So it will can be taken as Li cos theta. So in determining the efficiency of PV modules, this is one of the key factor that affect the efficiency. So in this session, we are going to solve the problems based on the solar insolation and that how it affect based on the Earth geometry, and how we can get this incident energy from this solar insolation. Now coming to this spectral irradiance. So spectral irradiance, as we know, the sun has having this electromagnetic radiation of different wavelengths, and each wavelength has having a distinct power level. So on this y-axis, we are having this spectral irradiance, and the x-axis, we are having this lambda wavelength. So now how we can get the solar insolation from this spectral irradiance plot? So we have to integrate this spectral irradiance plot with respect to wavelength. So such that we will get the solar insolation, and the unit of solar insolation is kilowatt per meter square. So what is solar insolation L? It is the accumulated effect of all wavelengths together, that will give the solar insolation. Now coming to this important terms that we have to know while solving the problem. Some of the terms related to solar irradiation geometry are latitude angle, that is phi, longitude angle lambda, declination angle delta del, and this hour angle omega. So from this right hand side plot, we can see these various parameters like hour angle, this declination angle, latitude angle, that is with respect to this earth centric coordinate system. And here if we see on the surface of earth, where we are considering this horizon plane, this horizon plane is nothing but it is the horizontal plane through the eyes of the observer. So here this is z, that is unit of z, that this is zenith angle, and zenith angle that is passing through the center of earth, and this is normal to this horizon plane. And if we consider this south and east side of this horizon plane, then it makes azimuth angle with respect to solar insolation line, and this zenith angle theta z, that is making with this solar insolation line with this zenith line, and azimuthal angle that is making gamma s with respect to south of this plane with the insolation line that is inclined with this horizon plane. And this left hand side, from here you can get this idea of latitude angle or longitude angle. Now coming to this important term, declination angle. So declination angle, from this expression we get, we know for the declination angle is that 23.45 sine 2 pi n minus 80 upon 365. So this declination angle varies from minus 23.5 degree to plus 23.5 degree. So now here one question comes is that when this declination angle becomes zero. On what days? The declination angle becomes zero. So this declination angle is the angle with respect to this equatorial plane, to this solar insolation, and it is taken positive if we go anti-clockwise, and it is taken negative if we go clockwise. So what do you mean by 21 upon 3 and 21 upon 19? Okay, 21 upon 9. So I am asking this on what days the declination angle becomes 0. Can anyone reply? You can type your answer in the chat box or you can speak also. So yes, Kegar has replied correct. So this angle becomes 0 on the equinox days because this angle is with respect to this angle is of solar insolation with respect to this equinox line. And equinox, we know that equinoxes when the sun is directly with the equatorial plane. So there are 4 special days that you have to remember. You have to know. Four important days that has that has uh, that has meaning. So how you can remember? So starting from January, February, then we have March. So on March 21st, we will get this spring equinox. Where the sun is directly in line with the equatorial plane. And then we are having April and then May, then June. So June 21 is the summer solstice. Summer solstice. And then July, August, 2 month gap, and then again in September 21 we will have again equinox. So this equinox is autumn equinox. Somewhere in the other textbook it is may written 22 or 23, but for easy remembrance we have considered 21. And then October, November, after 2 month gap, again we will having winter solstice. December 21, winter solstice. So if on these 2 days, a spring equinox and autumn equinox, we are having this declination angle 0. And for summer solstice, that is June 21, we can say that it is having the maximum declination angle, that is plus 23.45 degree, 23.5 degree. And for winter solstice, this declination angle is minimum, and this is minus 23.5 degree. So these 4 days we have to keep in mind. These are very helpful while we solve the problem. So first comes is March. Means these are in 2 months gap. So January, February, there is no special day. Then March 21 come. It is a spring equinox. Then again 2 months gap, April, May. Then again come a special date, June 21, that is summer solstice. And then July, August, 2 months gap. Again September 21, it is autumn equinox. And then 2 months gap, October, November. Again in December 21, we having solstice. And based on the weather, it is winter solstice. So the answer is that for this on what days the declination angle becomes 0. So this is directly asked in the problem, verbal type problem at equinoxes. And we have just seen it happens twice in a year. One is a spring equinox and one is winter, one is autumn equinox. So a spring equinox is on March 21. And then September 21 is autumn equinox. And now you can also verify from this angle, del, del declination angle. How you can verify? Because if these terms becomes 0, 23.45 sine 2 pi into n minus 80, 365, then declination angle becomes 0. So in order to make declination angle become 0, this sine term should be 0. And when this sine terms become 0, either at, sorry, so we know this sine term, sine waveform starting from 0. So it is 0 and again it becomes 0 at pi. So the inside term, this sine 2 pi, so we have taken it in radian, sine 2 pi n minus 80 upon 365. So this should be 0 or pi. So in first case, we are taking 0, 0 radian. So when it becomes 0 at n is equal to 80. So n is equal to 80, how we will get n is equal to 80? So starting from January, so in January 31 days, and in February for an generally we consider non-leap year, so it is 28 days, and to make n is equal to 80, we have to take 21. So this denotes 21 March. And now for second case, we have to make it pi. So 2 pi n minus 80 upon 365 equal to pi. So pi get cancelled out. So it will be n, you will get 365 plus 160, 2n. So on solving, you will get n equal to 263. So now if you just want to get this day, so from 263 number of days, you will get September 21. So from the equation, you can also find, and you can directly from this picture, you can also directly find this when this declination angle becomes 0. Now coming to this insulation, how we can write the insulation at a certain point on the earth. So this extraterrestrial insulation deviates from solar constant due to variation in radiation plus minus 1.5% and variation due to Earth Sun path due to elliptic path, that is plus minus 3%. And this solar constant, we know that its value is 1.37 kilowatt per meter square. So if we want to write the extraterrestrial insolation, then it is LSC into 1 plus 0.033 cos into 360 n upon 365. And here n is the number of days starting from January 1st. This solar constant value is given by 1.37 kilowatt per meter square. So after getting this insolation, after getting this extraterrestrial insolation, this L, and why it is called extraterrestrial? Because this insolation is outside Earth atmosphere, and terrestrial insolation that we getting on the surface of the Earth. So this one is the extraterrestrial insolation. So
Sir,
now,
sorry for sir,
no, yeah,
sorry
you
for
can.
interruption. Actually, one basic question: insulation and irradiance. What's the difference?
Okay. If you see the insulation irradiance, then I think, you have asked the difference between insulation and irradiance, right? Who has asked this question?
Yes, sir. This is my question, Ramesh Kumar.
Oh, okay, Ramesh. So in my point of view, this irradiance, like this solar insolation, we are getting the terms of power, that is kilowatt per meter square. But irradiance, that that is having how you can say, that are electromagnetic waves, and that has uh, that they not means that is not how you can say. So I think you can how I can speak with this. So I will specify in better way in next class, insulation and irradiance, because if we irradiance, that I have to see. But if we see this insulation, that means it is having a this specified power, that's unit is kilowatt per meter square. But irradiance, that are electromagnetic waves, and there are many different types of irradiance. But this insulation terms that is related to this solar.
Because I am asking you because in solar industries most of the people are using irradiance term, not insulation using insulation. Yeah.
Okay.
No worry. We will
Yeah.
discuss after class after this session.
Okay. Okay. Yeah. That's I also saw many where means like in papers also they directly wrote this solar irradiance irrespective of the solar insolation. Yeah, correct. It might be same. I'm not confirmed. It might be same. Okay,
Sir,
all right.
what we
So
know is, hello.
yeah, just tell me.
Sir, what we know is insolation is basically the energy that we are receiving per area, and irradiance is basically the power. Theoretically, looking at their units, because that comes insolation comes in kilowatt hour per meter square.
But in this course, here we are seeing this unit is kilowatt per meter square, not kilowatt hour. That is energy, this incident energy.
Okay, sir. Okay.
So
Sir, I had
let
some
yeah,
doubts uh, about the week
yes,
2 course, sir. Can I ask now or
yes.
we'll take it at a later stage, sir?
No, no, you can ask. Otherwise, we may forget.
Okay, okay.
Yes,
In the series connection of the solar PV panels, we were
yes.
introducing a diode so that whenever there is a mismatch between the ISC and VOC, the diode will short circuit and negative power will not come into picture, sir. Am I right, sir?
When this protection diode you have not put, then this negative power will not come. But when you have protection diode, then it will bypass it,
Yes, sir. So in the
right?
lectures, there was a reason. Um, Umanand sir reasoned that the diode it is usually put in an array. It is put for an array, not for individual cells, because the cost implications are too
Yeah,
high.
yeah,
I could not
right, right.
understand that part, sir. What exactly, how the implications are high for this?
There are mentioned like this if you having this this diode across each PV module, then this cut-in voltage should be lower than your this PV, like 0.2, 0.3. So it makes costly for making that type of diode. For making that type of diode having cut-in voltage is like 0.2 or 0.3 volt. That makes it costly. So generally we are having diode that's a cut-in voltage is 0.7 volt like that. So that makes we have to put this protection diode across the module, not this PV cell,
Okay, sir. So
right?
there are two. One is forward diode for one cell, and the reverse diode for protection is there, sir. So the what you are saying is the rating of the reverse diode, which is used for protection, shall be the summation of the forward diode and the output voltage. Is that so, sir?
1 minute. We have to uh, we have to go through the circuit. So we can discuss after this session. That will be good for us.
Okay, okay, sir. Okay.
And who is asking this question? Can I
Sir,
know the
it's
name?
Preeti.
Okay, fine. So one thing you can also do, you can I have not mentioned my email ID. So you can mail me also if you have means like irrespective of class, you can also mail me. I can also reply there if I could not able to take it in class.
Okay, sir.
Otherwise, I will try my best to give the answer during the class. So this
Okay,
is
sir.
my email ID, sahilgaurav@iitg.ac.in. So you can write mail also, but I will try here during class to clear your doubts. Okay, now coming to this hour angle. So the angle, this hour angle is that angle through which Earth must turn to bring this meridian of the observer directly in line with the sun rays. And this hour angle is taken as positive if we are going towards the east sides, that is this sunrise. So this is the solar time noon, and if we go this towards sunrise, then this angle is taken positive, and 1 hour be considered as 15 degrees. So here, if we take this 12 noon to this 9 a.m., then this angle becomes plus 45 degree. Now, if we go this side to the best, then we are having this hour angle negative, and if we go this 3 p.m., then its angle is minus 45 degree. So the day of length doing this locality on the equator is 12 hours. So this hour angle is made with respect to the locality on the equator. Now we want to know this sunrise and sunset angle for a specific location. So how we can know? We can use this expression LZ equal to L cos delta cos omega cos phi plus L sin delta sin del sin phi. And from this expression, we can find this sunrise angle and sunset angle. So at sunrise and sunset, we know this theta z is pi 2. So LZ you can write L cos theta z. So on putting theta z equal to pi by 2, you will get this omega SR angle, and that will come as cos inverse of minus tan del tan phi. And sunset angle will be this negative of sunrise angle, because it is symmetrical to this 12-hour noon. Now, how we can find the length of day? We can find the length of day as it is twice of the sunrise angle, and the sunrise angle we can write as in hours 12 upon pi into omega SR hours, and we know omega SR is cos inverse of tan del tan phi. And the next important expression is that daily energy incident on a horizontal flat plate. So the daily incident energy on a horizontal flat plate is denoted by this expression H naught, and it is equal to 24 L upon pi cos del sin omega SR plus omega SR sin phi sin del, and its unit is kilowatt hour per meter square per day. So it's here this another term comes inside this daily energy incident L and omega SR. So L we can write, we have seen the expression for L, that is LSC 1 plus 0.033 cos 360 n upon 365, and omega SR is cos inverse minus tan del tan phi. So these are all the summary for this assignment number 3. So if we know this expression and the important points, you are easily able to solve this assignment 3.
Sir, can you brief once again of the about the angles, all the angles?
Yeah. So here from this solar geometry figure, you can you can get this Dale angle, declination angle, that mainly depends upon the this time of year. And the expression you have to remember, this Dale is equal to 23.45 into sine 2 phi n minus 80 upon 365. And this hour angle that depends on the time of day. And hour angle you can find from the time of a day. And this phi is the latitude angle. So depending upon the position on the earth, we can get the latitude, and that this latitude generally given in the equation. And zenith angle, if we are having solar insolation on this horizon plane, so the angle making from this zenith line with the insolation line, that is zenith angle. And in this current assignment, there is no need of this azimuth angle, but this azimuth angle is the angle with respect to the south of this horizon plane, and it is angle making with this insolation line lying down this horizon plane. So these are some of the important angles that we have to take care. So it is very easy, miss, in this current assignment, not that much, miss, you need to just go through all the key terms and all the key expressions, and you can easily solve this current assignment. So now coming to this, till here any doubt?
No, sir. Thank you.
So the first, I am writing down this one question by insolation and irradiance. I think it might be same. So, but I will clarify this. What is the exact difference? And the second question, Preeti was asking about this diode. So let us come to this first problem. So on which day of a non-leap year does the maximum insolation level occur for an angle of 18 degree found between the insolation line and the equatorial plane of the Earth-centric coordinate system? And the options are 2nd May, 22nd June, and 11th May and 11th June. You can solve this problem and type your answer in the chat box. So this maximum insolation level occur for angle of 18 degree, and this 18 degree is given what? So can anyone tell? This 80 degree is given, it is found between the insolation line and the equatorial plane. So this is the equatorial plane. So this is insolation line. So what is this angle called? Can anyone tell? Can anyone tell what is this line angle called? Yes, declination angle. So this
Delta.
is del, right? Yes, Kager. So this declination angle, we know the expression for this declination angle. So this is 23.45 sine 2 pi n minus 80 upon 365. So this del is given as 18 degree. So from this data, we can find the n. So 18 degree into 23.45 sine 2 pi n minus 80 upon 365. So it is 0.766. So 0.766 into 1. So we have to take this sine inverse sine 2 pi n minus 80 upon 365 is June 20. So Prabhakaran, this is incorrect. So sine inverse of 0.7666 is 50.138 degree. So since this is in radian, inside is radian, so we have to take it in radian only. Sine inverse of 0.7676 will give you 0.875 equal to 2 pi n minus 80 upon 365. So into 365 plus 80. So upon solving this, you will get n equal to 130.8. So approximately equal to 131. So n is equal to 131. Which date it denotes? We have to find. So we have n equal to 131. So first we subtract the January month days. So it is for Jan month. So we will get 100 days. So again we subtract, since it is a non-leap year. Non-leap year means we have to consider February having 28 days. So again subtract minus 28 for February. So we will get 72. Again subtract 31 for March month. We will get 41, and upon subtracting April, we will get 11. So we are getting 11. So this denotes that 11 of May. The correct answer is 11 May. So any doubt? 1 minute. You can see the next problem. Hello. Yes, sir. Good evening. Yes, sir. Yes, sir. Oh, yes, sir. I will solve for this. Yeah. Okay. Yes, sir. Yes, sir. 1 hour. Yes, sir. Okay, sir. I'll- So now coming to the next problem. So this problem is that if an angle found between the zenith axis of a local coordinate system and the median axis of the earth coordinate system is 35 degree, then how many hours are there in the longest and shortest day of a non-leap year respectively? And the options are shown over here. So what are the things we have given here? So this zenith axis of a local coordinate. Zenith and the angle formed the zenith axis of local coordinate system and median axis of the earth coordinate system. So this angle is the latitude angle. So given angle is the latitude angle that is given by 35 degree. Now they are asking that how many hours are there in the longest and shortest day of a non-leap year. So longest day, we know that this longest day is happening on summer solstice, that is on 21st June. Longest day on 21st June, that is happening on summer solstice. And this for summer solstice, this Dale angle, we know that this is 23.45 degree. So has taken as 23.5, so we can take it at 23.5 degree. Yes, Prabhakaran, this is correct. D is the correct answer. For this question number 2, D is the correct answer. And shortest day, on 21st December, winter solstice, that is happening for on 21st December, and for this inclination angle is minus 23.5 degree. So we have to find the number of hours. So considering the first case, longest day. So we know that length of day expression, length of day expression is 24 upon pi cos inverse minus tan phi tan del. So just substitute all these values. 24 upon pi cos inverse minus tan 35 degree tan of 23.45 degree. So you will get 24 upon pi into 1.2622. So it will be 14.35 hours. So here from this longest day only you can get the answer 14.35 hours. So let us solve for this shortest day also. So for shortest day, that is happening on 21st December. So length of day will be 24 upon pi cos inverse. So previous one it is minus, so it will come as only positive. So this term is 0.3037. So simplifying this, you will get 9.64 hours. Now coming to the next problem. Here we have to calculate an equivalent standard insolation time in hours, considering the standard insolation as 1 kilowatt per meter square. Form an insolation graph given in the below figure for a day. So first we will find the total insolation energy.
Sorry, sir. Actually, in second question, I am not
Yes.
getting the answer. Uh,
So
can you solve?
where are you getting?
Yeah, actually, I'm trying to solve this question, but I'm not getting the answer.
So I think you are doing.
24
I think
by pi.
yes. So if you uh, so just careful about the degree and radian. So like if you are solving this tan 35 degree into tan 23.45 degree, then you will get
38.56.
this cos inverse of 0. Minus 0.3037. Till here correct? You are correct. Till here no problem. You are getting this cos inverse minus 0.3037.
No, I'm getting 38.56.
How will you get 30?
Tan 35 degree 0.47.
So this value is less. Tan 45 is less than. You just
Tan
careful about degree and radian. So you are getting putting values in degree or radian. Tan 35 radian or tan 35 degree.
tan 35 degree.
Yes. So you will get this value only because tan 45 is 1. So this value will be less than 1.
Yes, less than 1. Yes.
So that's why we are
minus
getting 0.3037.
1035 degree. 1035 degree answer is 0.47, and 1023.45 answer is 8.896.
1023.45.
8.896.
No, it is coming at 0.4347. 1023.45 degree, it is coming as 0.4337.
That means you are converting 23.45 degree to radian.
No, I am just writing it again. So 1035 is
Minus
0.7,
point
and then 1023.45 is
0.47, sir.
0.4347. Yeah, if you put 23.5 degree, then it will come as 0.4348.
Actually, sir,
Now you are getting this.
1035 is value is 0.47.
No, you are doing somewhere mistake. 1035 will come as 0.7, and this 1023.45 is 0.4347. So upon multiplication, you will get 0.3037. Now, if we take inverse, then you have to get the answer in radian, not in degree. So like if you take this inverse, and if your calculator is set in degree, so you will get wrong answer. Like if you do cos inverse minus 0.3037, then it is coming as 107 degree, but you have to write in the radian. So again again so again converting radian, you will get 1.2622 radians. You just again go through it again, means carefully. I think you are able to get it.
That means I have to change degree to radian.
Yeah, means like this 24.24 upon 5, it is in radian. So you have to, this value should be in radian. This
Okay, okay,
value
got it.
you have to, this value you have to
Got
get
it.
in radian.
Got it. Thank you, sir.
So shortest we have found it is 9.64 hours. Now the next problem we are having this, we have to find the equivalent standard insolation time. So first we find this insolation energy from this insolation graph. So how we can find the insolation energy, total insolation energy per day? This is integration of L into L d omega for a day. So we have to take the area of triangle. So it is half of this base is 12 and height is 1.42. So it is coming as 8.52 kilowatt hour per meter square per day. Yes, Prabhakaran, you are correct. Correct answer is B, 8.52. And this standard insulation is given as 1 kilowatt per meter square. So to get the, here they are asking about the time. So we have to divide with this total insulation energy upon a standard insulation. Therefore, this equivalent standard insulation time equal to installation total insulation energy total insulation energy upon standard insulation. So it is 8.52 kilowatt hour per meter square per day upon 1 kilowatt hour per meter square. So the answer is 8.52 hour per day. So you have to play with the units also. Here they are asking about in hours, equivalent standard insulation time. So it is 8.52 hour. So what the significance of this time? Like here, this plot is given for a day. Now, if we want the same amount of insulation energy for a standard insulation, means of 1 kilowatt per meter square, then for an hour of like this one. So this is a standard insulation, that is 8.52, and this equivalent time. And the equivalent time, sorry, this is 1 kilowatt per meter square, and equivalent time is 8.52 hours. And this is 1 kilowatt per meter square. So for a standard insulation of 1 kilowatt hour per meter square, this 8.52 hour, the same amount will provide the same amount of insulation energy. So this equivalent insulation time is 8.52 hour. So the correct answer is 8.52. Now coming to the next problem. So from the problem 3,
Sir,
you have
just a minute.
yes.
Please. Yes. Just a minute, sir. Done, done sir. Done.
Okay. So now from the next problem is that from the problem number 3, you have to calculate the number of solar panels needed to satisfy a peak load of 20 kilowatt hour if each solar panel has a rating of 100 watt peak power per solar panel. This is a very easy problem, and there is no need of any expression or any equation. You have to remember from this from the uh, from the question you can easily solve. From the data you can easily solve the problem. So here you have to find the number of solar panels. number of solar panels equal to what, and the peak load is 20 kilowatt hour, and each solar panel rating of 100 watt. Rating of 100 watt. So peak load, that this is the amount of energy required, and we have seen that this total insolation energy we are getting is that 8.52 kilowatt per meter square. That is the amount of energy we are getting from each panel. Yes, Prabhakaran, you are correct. 24 is the correct answer. Very good. So from the last problem, we have found that energy produced by each panel is eight five two zero watt hour per panel. So it is the amount of energy produced by each panel we got from the last problem. So we can write that number of panels equal to total energy required upon energy produced by each panel. So total energy required is 20 kilowatt hour. So it is 20,000 watt hour, and energy produced by each panel is 8520 watt hour each panel. So upon dividing it, we will get 23.47, so equivalent to 24 panels. So C is the correct answer. Yes, Pravakaran is only replying. Other one, please, all of you try. Don't just solve at the last moment. If you solve parallelly with me, and that will be helpful in your current assignment also, and in your final exam also. So the next problem is that what is what is the angle in degrees formed by the insolation line and the equatorial plane for the date October 2, 2023. So the angle between the equatorial plane and the insolation line So we know that, let us take it as equatorial plane, and this is insolation line. So this angle is the declination angle. So we have to find the declination angle. we know this declination angle expression is. So this is a numerical type problem. You have to give the answer in the, you have to type an answer in the box. So this is numerical type problem. So del angle is given by 23.45 sine 2 pi n minus 80 upon 365. So this is the declination angle expression. Now here only one thing is unknown. We have to calculate the n. And from the data, we can see that the data is given as October 2. So we have to, we can find the number of days from October to 2023. And this is a non-leap year. So the number of days in February will be 28. Yes, minus 5 is the correct answer, Prabhakaran. Very good. So this is a non-leap year. Therefore, you can find the n value. You can start from the starting also, and you can start from the end also. Like if you go from the starting, in January 31 days, in February 28 days, and in March 31, April 30, May 31, June 30, July 31, August 31, and then September 30, and in October 2. So if you sum up all this, it is 31 plus 28 plus 31 plus 30. So it is coming as 275. You can also find the n value from the end of day also. Number of days in a year, 365 minus 31 for December, and then 34 November, and in September it is 31st. So you have to 31st minus 2, then it will be 29. So it is for October. So from here also we will get 275. Therefore, this declination angle is 23.45 sine 2 pi 275 minus 80 upon 365. So you will get this value as 23.45 into minus 0.2135. So it is minus 5.007 degree. It is equivalent to minus 5 degree. So in the final exam also, some problems will be multiple choice problem, and some question will be numerical answer type also. It is not necessary that you will given with option only. So the range for this problem is given as minus range is given as minus 5.5 to minus 4.5. If you type your answer within this range, then you will get the marks. Now let us see the next problem. So calculate the effective insulation in the local centric coordinate system on the horizontal flat plane for a zenith angle of 40 degrees on March 20th, 2024. So here you have to find the effective insulation. So first, and what are the things are here they are given? They are, so first let us write what are the things they have given. So they have given this zenith angle. Zenith angle is given as 40 degrees. and they have put this date. From the date, we can find the n value. So 20th March 2024. So this is a leap year. So for a leap year, number of days in February will be 29. So for a then we will get the n value as January as 31st, February as 29, and March as 20. So 50, 51, and then 60, 60 plus 1, 20, 80. So we will get the n value as 80. Now to find the effective insulation, like on a horizontal flat plane, let us take this horizontal flat plate, and this is extraterrestrial insulation. And this is the effective insulation. So this is the zenith angle, theta z, and this is the extraterrestrial insulation. We have to find this one. We have to find this L effective. So we know that extraterrestrial insulation expression is 1.05. Yes, Prabhakaran, correct, very good. So first we find the extra terrestrial insulation. Will you please explain longest length of the day? So after solving this, we will see that problem. So extraterrestrial insulation is given by this L equal to LSC and into 1.0033 cos 360 n upon 365. So solar constant, we take it as, so LSC solar constant, we take it as 1.37 kilowatt per meter square. So taking it as 1.37 and 1 plus 0.033 cos 360 n is given as 80 upon 365. So this value comes as 1.3787 kilowatt per meter square. Now, what is the effective insulation? Effective insulation, this you have to take this extraterrestrial insulation that is lying on this normal surface, normal to the plane. Then this is L cos theta z. 1.3787 kilowatt per meter square. Cos theta z is cos 40 degree. So it is 1.056 kilowatt per meter square. And the range for this problem is given as 0.99 to 1.35. Will you
Sir,
explain from the 20? Yes.
actually, in this question, how to understand this question? We have to find out the extra terrestrial insulation, because there is no mention in the question for the extra terrestrial insulation.
Because you have to, they are telling about the effective insulation. Effective insulation means that is normal to this horizontal flat plane. So, and this zenith angle is given. So how we can find this effective insulation? So to find the effective insulation, we need to find this extraterrestrial insulation. I have shown in the starting slides. Yes, this one. Did you got this point or not? Ramesh, who is asking? Ramesh, right?
Yes, sir. Yes, Ramesh.
So someone was asking about back problem. Will you please find longest length of the cruise 24 upon pi 1.262? Rajnikant. So this one. Yes, what is the doubt, Rajnikant, here? So this is very simple. Longest day, we know this is on summer solstice. So you know from Dale angle 23.5, or you may take somewhere it is taking a 23.45. So either bis, whatever bis you can take. So Dale angle is 23.5. We know the latitude angle. So from there you can calculate this, the length of day, the number of hours. And be careful about the degree and radians values. Either means whatever calculator you are using. So be careful. Here you can also substitute this degree into radian, 23.5 and 35 into radian. And now you set your calculator in radian and just put all these values. So you will get directly answer in the number of hours. And here if you put this degree, then you have to first set the calculator in degree form, and then after getting this inside term of cos inverse, you have to put again this in radian form to get the answer of cos inverse in radian. So if you get the answer as 1.2622, so you have to just multiply this with this, you will get the number of hours in a day. So just be careful about the radians and degree. And anyway, if you are getting just not the answer in a range, like the number of hours you are getting more than 24, then it is more than uh, more than 15, 16, then it is obvious incorrect, because number of days cannot be that longer. So the number of so you have to check that you did somewhere a mistake. Now let us see the next problem. So this is, in this problem, here this power density is given, and you have to compute the solar insolation kilowatt per meter square for the graph here shown in the figure, where this wavelength is given L and the power density are shown on the XY respectively. So you have to compute the L. So this is very simple problem also. Here just you need to calculate the area. So here you need to compute this area. This area and this area. So power density unit is kilowatt per meter square per nanometer, and wavelength is given nanometer. So if you took the area, you will get the insulation. So LS is given as insulation L is given as integration of PS into T lambda. So this is power density. So we can write L as, so the area for this first triangle, half into base is 450 minus 10, that will be 440 nanometer, and then height is 1.25. Yes, correct. 3.37 kilowatt per meter square. Very good, Prabhakar. So this is the area of first triangle. Now this area of rectangle we can write as 500 into 1.25. And now we can find the area of top triangle. So it is half of base is 500 and height is 1. And this last one, this area of triangle, half of 450, 100 minus 950. So it is coming as 3550 and height is 1.25. So you will get 275 plus 625 plus 250 plus 2218.75. So you will get 3368.75 watt per meter square. So the answer is 3.37 kilowatt per meter square. So this is the correct answer for this problem. So for the current assignment, one thing I want to tell you that this assignment is easy because here you only need to know the expression. If you know the expression and you know how to use, then you will get easily marks. Now let us come to the next problem. The next problem is that you have to compute the amount of daily energy in kilowatt hour per meter square per day available with a declination angle of 45 degree on the equator line for the day 5th September 2023. So this is the first problem for the incident energy. So we know the incident energy expression. Solar incident energy expression that is given by so let us first write what are the things given in this problem. So declination angle is given as 45 degree, and since this is on equator line, so equator line, that means latitude is given as 0. So latitude angle phi is given as 0 degree since this is on equator line. And from the time in a year, means from the date given in a year, we can find the N, 5th September 2023. So N is this 23 is a non-leap year. So N is equal to 365 minus 31 for December, and November is 30, and October is 31st, and September is 30. 30 minus 5, that is 25. So 365 minus 31 minus 30 minus 31 minus 25. So it is coming as 248. So these things are given. Now we have to, from this data, you have to find the amount of daily energy incident for the day 5th September 2023. So we know the expression. So Rajnikant, he has doubt here. Okay, correct. This is not coming as 14.35 hours. Yes, there is a mistake. I have put in the wrong. Thank you, Rajnikant. So this value is not 1.2622. This value is so this value is not 1.2622. So this value is 1.87933. Thank you, Rajnikant. Thank you for this identifying this mistake. Let us come to this problem. So this we know this solar incident energy on a horizontal flat plane. We know the expression is H naught equal to 24 upon pi into L cos phi cos phi cos del into sine omega SR sin omega SR plus omega SR sin del sin phi. So this value is coming as in kilowatt hour per meter square per day. So for this problem, first we need to find the L. Extraterrestrial insolation. So it is 1 plus 0.033 cos 360 n upon 365. So LS, this is 1.37 into 1 plus 0.033 cos 360, n is 248 upon 365. So it is 1.37 into 1.0298. This one will give you 1.411 kilowatt per meter square. This extra now we have to find this omega SR. Omega SR is cos inverse minus tan phi tan del. So since latitude angle is 0, so cos inverse is 0. So it will give you pi upon 2 radians. Now we put all these values in H naught, we will get the amount of daily energy. Now shoot this all values in the H naught expression. So H naught is 24 into L. L value we got 1.411 and into pi cos phi is cos 0 is 1 and cos delta cos 45 is 1 upon root 2 and sin omega SR is 1. So and this term will be 0 because sin phi is 0. So you will get 24 into 1.411 upon pi into root 2 pi. So it will be coming as 7.62 kilowatt hour per meter square per day. Till here, any doubt? Prabhakaran, Neeraj, Ramesh, Deepak, Sangvi, Praveen, Rajnikant, Preeti, and Nikhat. So coming to the next problem. So length here you have to find the length of day on December 31st, 2021 in the city of Sydney. And here this angle is given latitude and longitude. So you have to find the length of day. So what is the length of day? We have seen in the starting slides. Length of day is 24 upon pi cos inverse tan phi tan delta hours. So first we find the declination angle and this latitude angle. Latitude angle is given in the problem. So let us first find the declination angle. So what are the things given here? December 31st, 2021. So from here we can find the n. So since it is the last day of a year, so n will be 365 and it is a non-leap year. Now this latitude angle we will find pi. So this is given as south. In the south, we take the angle as negative. So it is 33.8688 degrees south. So this will be the negative minus 33.8688 into pi upon 180 degree. So be careful, if it is given as north, then we will take it as positive, and if it's taken south, then we have to take it as negative. So this is the sign convention. So phi is given as minus 33.8688 in degrees. So we have to convert in radian. So we get it in radian by multiplying with pi upon 180 degree. Now we can find the declination angle del. So these things are given in the problem and we have to find the length of day. So first we will find the declination angle del. So it is given by 23.45 sine 2 pi n minus 80 upon 365. So it is 23.45 sine n is given as 365 minus 80 upon 365. So this will be 23.45 and sine of this give you minus of 0.98. So this will give you minus 23.0116 degree. In order to convert in radian, so you have to multiply with, yes, correct Prabhakaran, it is 14 hour. Very good. So let us convert into radian. 23.0116 into pi upon 180 degree. So it will be in radian. Now we can write the length of day expression. It is 24 upon pi into cos inverse minus tan phi tan del. So here in this problem, we have converted all the angles in radian. So you just set up your calculator in the radian, you will get the answer correctly. No need to interchange. So it will be 24 upon pi into cos inverse minus tan phi. Tan phi is minus 33.8688 into pi upon 180 degree radian, and tan del is minus 23.0116 into pi upon 180 degree. So if you do calculation, then you will get 24 by pi cos inverse minus 0.285. So 24 upon pi into 1.8598. So this will be 14.20883 hour. And the answer they provided is 14.21 hour. So this is the correct answer. So here one important thing you have to keep in mind, that is latitude angle. If they are given in terms of, if the angle is given as degree south, then you have to take it as negative. If it is given degree north, then you have to take it as positive. Let us come to the next problem. So what is the total amount of energy in kilowatt hour per meter square per day available on a horizontal flat surface on the day 21st March at a place of latitude 23.5 degree north? So here this phi is given north, so it is positive. Considered extraterrestrial insolation hail is 1.38 kilowatt per meter square. So let us first write down what are the things given. 21st March. So 21st March, we know this is a special day. 21st March is a spring equinox. Right? 21st March is spring equinox. So on equinox, we know that this solar insolation line lies in the lies in parallel to this equatorial plane. So this del angle will be 0. So declination angle is 0. And we also know that this, if this on equinox days, this length of day and night is same here. So we can write that at equinox day, length of day and night is same. Therefore, this omega SR is pi upon 2. So this is omega SR we are getting pi upon 2. So from here also you get this omega SR angle, our angle, cos inverse tan del tan phi, since this declination angle is 0, that means cos inverse 0 is give you pi, cos inverse 0 will give you pi by 2 hours. So this angle will give you pi by 2 radians, sorry. So this will give you radians. If you want to convert in the hours, then it will be you have to multiply with 12 upon pi, then it will give you 6 hours. Now we have to again write this insolation. We have to write this the amount of daily energy incident, this in H naught expression here. So H naught expression is, and one thing also here they have given in the problem, it is that latitude. So latitude is angle given 23.5 degree north. So we have to take it as positive 23.5 degree. And this extraterrestrial insolation is given as 1.38 kilowatt per meter square. Now we will put all this expression in this amount of daily energy incident expression H naught. So H naught is 24 upon pi into L cos del cos phi sin omega SR plus omega SR sin del sin phi kilowatt hour per meter square per day. So since del is 0, so it will be 1 cos phi, we have to put 23.5, and sin pi by 2 is 1, and this omega SR is pi by 2, and sin del is 0. So whole this term will become 0. So we will get H naught as 24 upon pi into 1.38 and cos of 23.5 degree. So if you do simplification, then you will get 9.668 kilowatt hour per meter square per day. This is the answer. Now let us see the next problem. Refer to the previous question. What is the approximate amount of perpendicular insulation at that place in moon? So this perpendicular insulation is extraterrestrial insulation into cos theta z. So this L is given 1.38 kilowatt per meter square, and what is this cos theta z?
zenith angle.
Yeah. So zenith angle, correct. It is zenith angle. So, so since this angle, zenith angle will be equal to latitude angle, phi plus delta. So phi is 23.5 and del is 0. So it will be cos 23.5 only. Zenith angle will be 23.5 degree. So it is coming as 1.38 into 0.917. So it will give you 1.27 kilowatt per meter square. Now let us see the next problem. So
Sir,
here
how
this
become
spectral,
zenith angle is 23.5 degree?
because this place is at equinox. So this place is at equinox, means like at equator. So this is the insolation, and this is the insolation, and so this angle is zenith angle. So uh, uh, what is the perpendicular insulation with respect to this extraterrestrial insulation? That is cos theta z, because since this point lies on the equatorial plane. If it is not lies on equatorial plane, then this angle will be not, theta z will be not equal to phi. So here theta z is the angle equal to latitude angle. Since this point is at equinox. So let us see the next problem. We have less time. So this problem, this spectral irradiance of an illuminating light source can be related to its wavelength by the following equation. And it is found that source spectrum contains wavelength in the range from 400 nanometer to 7 nanometer only. Then what is the insulation coming out of the surface? So for first case, that is for 400 nanometer, for lambda for x is equal to 400 nanometer, we will find the PS. PS is 0.01 into 400 nanometer minus 2. So it is given as 2 watt per meter square per nanometer. And for x is equal to 700 nanometer, this PS will come as 0.01 into 700 minus 2. It is given as 5 watt per meter square per nanometer. Now if we plot it on this spectral irradiance versus wavelength, PS versus wavelength, watt per meter square per nanometer, and this is lambda. So this first point is 400 nanometer, and this is 700 nanometer. So this is 2 watt per meter square per nanometer and 7 watt per nanometer square. So we have to find the insulation. So we know that LS is area of this plot, area under this curve. So we have to find this area. We know this LS, L is the integration of PS into d lambda. So we will get L value as, so first we can find this area of rectangle. So it is 2 into 300 plus top rectangle. So top triangle. So half into base into height. Base is 300, height is 3. So it is coming as 1050 watt per meter square. So this is the answer. Now let us see the next problem. So the next problem is given that it's a square P panel having total cell area of 0.1 meter square is mounted on a movable mechanism having a single degree of freedom for its movement. This movement is fluctuant at its center along the diagonal of the P panel. The tilt angle P panel is considered 0. when the PV is placed horizontal, the PV panel efficiency of, so this tilt angle will be taken care in the subsequent classes. For this NPTEL course, the PV panel efficiency of 15% respective angular tilt. What should be the tilt angle of PV panels? So the PV produces half of the maximum output power possible for a particular amount of insulation, assume the sun is at vertical position. So when this PV panel is kept horizontal, the peak power output will be, so the case 1, panel is kept horizontal. In that case, maximum power is efficiency into insulation, and tilt angle is 0. So cos 0 into area. So PM1 is efficiency into L into A, and in case 2, then the panel is kept an angle of A. So PM2 will be efficiency into solar insulation, and cos A, area will remain same. So PM2 will be N into L into cos A into area. Now, in this problem, it is given that we have to make PM2 equal to half of PM1. So in order to make half of PM1, PM2 is efficiency into L into cos A into A, and half of efficiency into L into A. So this A tilt angle will be coming as 60 degree because cos A is half. So the correct answer is 60 degree. Now, referring to the previous problem, what should be the tilt angle of PV panel degree to generate a peak output power of at least 50 watt, assuming solar insulation of 1 kilowatt per meter square. So this PM is given as if into L into cos A into area. So it is given that PM should be greater than 50 watt, and L is given 1 kilowatt per meter square, and area is given as 1 meter square. So PM should be greater than 50 watt. So let us take it like this, equal to efficiency is given as 15%. So 0.15 into 1000 into cos A. So substituting all these values, cos A will be greater than 50 upon 0.15 into 1000. So A will be less than cos inverse 50 upon 150. So A will be less than cos inverse 1 upon 3. So A is less than 70.53 degree. This is the answer. Now the next problem. Calculate the amount of solar insolation incident at noon 31st March 2021 on horizontal flat plate located at latitude angle of 12 degree. So latitude angle given as 12 degree, and n we can find from 30 March 2021. So it is non-leap year 31 plus 28 plus 13. So it is 72. So we can find the declination angle delta del. So it is 23.45 sine 2 pi n minus 80 upon 365. So n is 72, you will get it as minus of 3.22 degree. And extra terrestrial insolation is given as 1.37 kilowatt per meter square. Our angle is 0 since it is at noon. Latitude angle is given as 12 degree. Now we have to find the solar insolation LZ. So LZ is L into sine del sine phi plus cos del cos phi cos omega. So we will get this LZ equal to 1.37, and if you put all these values, you will get inside 0.965. So it is 1.321 kilowatt per meter square. In watt per meter square, 1.9 watt per meter square. Now the last question is that for the year 2023, the value of declination angle is negative on which of the following days? So declination angle is positive if we go towards, this is multiple select question. There are multiple answer can be correct. So here so we know that equinox days is this March 21st and this September 21st. So when this declination value is negative, if we go from this equinox to summer solstice, then it will be positive, and if you go from this equinox to this winter solstice, then it will be negative.
A, B, C.
No, incorrect. So from December to March, so whatever the months lies between this, like between December 21st to March 21st, all will be in negative value. And from March 21st to June 21st, it will be positive again. And for this June 21st to September 21st, it will be positive. And from September 21st, from September 21st to December 21st, it will be negative. So whatever the dates lies between below, that will having negative, the declination angle is negative. So what are the values lies between this? So January 21st lies between this point. So A will be the correct. August 15 lies between the positive range because it lies between this March to June. So it is not negative. September 5 is also lies between June 21st to June 21st to September 21. So it is positive. Now October 2, it is negative because this live is September 21, December 21. And November 24, November 14 is also lie negative, and December 25 it also lies with this negative range. So this December 25 will be negative. So you can say that whatever the values lies between this December 21st and March 21st, this will negative declination angle, and this between September 21. So you can directly say that this September 21st to March 21st, all having the negative value, negative declination angle. So the correct answer is A, D, E, F. So this was the last problem for today's session. Any doubt till here? Thank you all for attending the session, and we will meet at the same time on next Sunday for the live session number 4. So I will upload today's recording lectures on YouTube also. You can watch there also, and you can ask your doubts there also. Thank you all, and good night.
Thank you, sir.